So first I want to say thank you for all showing up to the first talk of the year. I know everyone's pretty tired and it's already like pitch black outside, so I think everyone kind of just wants to go to sleep. Yeah, and I'm not going to spend too long. I'm going to pass over to Kate quickly, but I just wanted to remind everyone that the EGM is happening after this. We're going to head probably around 7:30 or so to Chaplin's, and the upstairs is booked out. So we're running for first year rep, an efficiency OCM, and an admin officer. If any of those don't really make sense, we'll talk about it more afterwards at the EGM. But we would say go. If you're not going to run, at least go for the pints, but also please run. Yeah, so Kate, do you want to?
Yeah, sure. So good evening, everyone. Some of you I recognise that this is your third time listening to me today, so thanks for showing up. So in this talk I'm going to focus a little bit more on the research I do into extreme explosions and catastrophic collisions in the universe. So I'm an astrophysicist in the School of Physics. And yeah, I'm going to tell you a little bit about what I do with my group and the kind of topics we explore in transient astronomy. So the first thing you might ask is, why do we care about extreme explosions or things that collide in the universe? And so they have impact on a number of different areas of astrophysics. One of them is in the nucleosynthesis of heavy elements. So things like iron are produced in type 1a supernovae that I'll mention. These about half a solar mass, about half the mass of the sun, is produced in iron in each of these explosions. And then there are other types of explosions that I'll also discuss, so like compact object collisions. We think now that these are the sites for our process, nucleosynthesis. These are heavy elements in the periodic table, so things like platinum and gold are produced in these explosions. So this is a recent confirmation that we've been able to see this. They also power feedback dynamics in galaxies. You can imagine these very energetic explosions of stars occurring in the universe, and these can drive outflows in galaxies and cause different other like star formation to occur. And also they were essential for the discovery of dark energy. So dark energy was discovered at the very end of the last century, and so this is a mysterious quantity that we know makes up the vast majority of the universe, but we still don't understand its origin. And so we can try and study this with type 1a supernovae. So this is a particular type of exploding star. So they're produced from a white dwarf, and they make excellent standardizable candles. So they have, so we can calibrate their light curves, so how bright they are, and then we can use them to measure distances in the universe. And so from using these supernovae, you can see that the latest results suggest that about 70% of the mass energy of the universe is dark energy. And so we don't really understand what dark energy is. It's some mysterious quantity in the universe. So it was originally Einstein's cosmological constant. So this is one hypothesis for it. So some kind of vacuum energy that's producing something that acts against gravity to cause the expansion rate of the universe to accelerate. Dark matter we know more about. This occurs, it's influenced by gravity, and so we can see it around galaxies in the universe. And we know that makes up about 30% of the universe. And then the remaining approximately a little bit less than 5% of the mass energy of the universe is ordinary stuff. The tables, us, the planets, the galaxies in the universe. So it's actually a very small percentage. And so if we want to use type 1a supernovae, so SM1A is the shorthand way of writing this, we want to use them in future surveys. We're limited by how well we can calibrate them, so like how well we know the filter responses of telescopes, or how we can calibrate instruments very precisely. But the one that I'm more interested in is the lack of knowledge of how they actually explode. And so even though we use them to very high precision in the universe to try and understand the origin of dark energy, we don't actually know what they are. So skip that. Okay, so one way that we think that a white dwarf might explode is from accretion from a non-degenerate companion star. So some of people may have seen similar movies like this earlier today in the lectures. It just coincidentally, it's a very similar topic. But this is a white dwarf exploding through accretion, so it gains mass from its companion star. It approaches something called the Chandrasekhar mass limit, which is about 1.4 times the mass of the Sun. That's the limit that can support itself against electron degeneracy pressure. And when it goes over that, or close to it, a runaway thermonuclear reaction occurs in the white dwarf. This is a carbon-oxygen white dwarf. And it can runaway reaction completely unbinds the star and it explodes as a supernova. And this is what we can measure as light. So this is one hypothesis, the original hypothesis for how a type 1a supernova exploded. But since then, previously there were also models of double white dwarf mergers. So in this case, you have two white dwarfs in a binary system that can in-spiral and then collide or merge and produce an explosion. So they're kind of like the two broad classes. Now within those, there are a lot of methods of exploding these stars, different detonation processes in the stars to try and explode them. But generally, they fall into these two different categories. And so we use them for cosmology. We calibrate them. They're essential. But we still don't know which of these two ways, the single star or the non-degenerate star as the companion with accretion or some kind of merger. And so we want to try and go out and see if we can figure out ways of distinguishing between them. And so one way we can do this is using supernova light curves. And so this is a light curve of a supernova. So this is a flux here and then a timeline from explosion. So it rises to peak in about 20 days. And the whole light curve is powered by so a lot of nickel. I said iron is produced in the explosion. That's radioactive nickel, and it decays. And it's the decay of this nickel that powers the light curve. So you might think it's like the explosion itself, but it's not. It's actually the radioactive decay that produces this luminosity, and then it fades away over time. And so if we want to try and understand or try and figure out what's exploding as a type 1a supernova, we have to try and use different methods of understanding them. And so one way we do this is with really early observations. So we say early by meaning really soon after explosion. And so in these early times, you can imagine if we have our star like the Sun, so like a big non-degenerate star, when the supernova ejecta runs out into space, it might collide with that star. And so it might hit into that material. So you won't get that in the merger scenario, but it might hit into that companion star, and actually this collision or this shock puts an extra boost into the light curve, and you can see this as an additional flux in the early light curves, so like from the collision itself. You can also look at late times in the light curves, properties, subtle properties of the different progenitor channels impact how the internal structure of the star is. So I won't discuss that more. And then, you can also look for signatures of this companion interaction. So what's the properties of the companion star at late times as well. And we also know type 1a supernovae, because they're old systems, so white dwarfs are old stars, they can occur in old stellar populations, this is like an elliptical galaxy, or they can occur in a spiral galaxy. And so we see them in both, and so this can give us hints about what the progenitor scenarios are. So the problem with trying to understand how they explode was, originally when people realized they could be used for cosmology, they went out and they just said, okay, our telescopes aren't that good, we want to try and get as many of these observations as possible. And so they started to take data points like this in the supernova light curves. They found a new event on the sky and they started to track it to try and follow its evolution with time. But you can see, typically they had about a 3 to 5 day, what we call cadence, of time between each observation. But it turns out if you want to try and do studies of what's going on, so this companion star interaction, you really want to be looking at these really early phases. And just in previous data that wasn't possible, because we weren't getting the high enough cadence, we weren't getting the observations close enough together to be able to track any kind of additional bumps. So we have our light curve, and then just to say again, for this companion interaction, what we would be expecting, so if you're exploding white dwarf here, and some non-degenerate companion star, then when it runs into it, you would get a shock interaction and this additional luminosity in the light curve. So people want to try and figure this out and see if they can actually observe this. So we did this with the transient search facilities around the world. So you can see different telescopes marked. All of these are transient discovery machines. So they're in very nice exotic places. We've got Hawaii, Chile, Canary Islands, The Sticky Transient facilities in California. As an astronomer, you do get to go and visit these telescopes. I've seen this Vicky Transient facility at Beach Black Gem in Chile. It's very nice going observing. I'd highly recommend it if you do a PhD in astrophysics. But the one telescope I'm going to focus on now is this Vicky Transient facility because I'm involved in this survey. And so it's running in the Palomar Observatory in California. It's got a big camera, so it's 47 square degrees. So it's it's one of the largest of these transient surveys in the world. And it's observing a very high cadence. So again, this means multiple times. So here it says six times per night. So previous surveys were like every 3 or 5 days. Now we're down to 6 shots a night. And so with this, we can get data for very early light curves of type 1a supernova. So you can see some of these light curves here. So this is just the flux and magnitude as a function of time. So they get brighter and then they decay away. So we're getting loads of this early data that we then can try and compare to models that suggest whether it's a non-degenerate companion star or not. So we collected about 130 of these events, and we've got another 500 or so now that are currently being analysed. So what can we do then? We can look at these very early light curves. So here you've got, so this is time from explosion in days, and then we have the absolute magnitude again. So this is just a range of different supernova light curves, but for a normal type 1a supernova would lie here, and then all of these events that are shown here have some kind of excess as early times compared to what we'd expect. And so this suggests for these ones, we call them bumps in the light curves, and these suggest its interaction with a companion star running into this material. And so this suggests it's a non-degenerate companion star for some of the events. And so this is one way, this is just highlighting one way we can try and understand what's actually exploding as a type 1a supernova and then improve the future cosmological measurements. Along with that, when people went out to try and understand the supernovae or take observations, so we found a lot of normal type 1a's you'd use in cosmology. But we found unexpectedly lots of little faint and fast evolving supernovae. So they were a few orders of magnitude fainter in their flux and their peak, and they just appeared as little blips and then disappeared, so maybe on the order of a few days. And we weren't expecting this, and so theoreticians had a field day. They went out and tried to come up with the most exotic explosions that they could from different things. And so, for example, there's disruptions by black holes. So you can have, so they're all white dwarf. We think these are all white dwarf explosions. You have some kind of white dwarf that gets close to an intermediate mass black hole, gets stripped and like stretched, and then this causes something that we can see. We can also have a white dwarf with a thin little shell of helium on the surface. This can be detonated by accretion from a companion star. This could also produce a small little explosion. Or we could have some kind of white dwarf neutron-star merger, which has been predicted with jets involved, and this could also produce some of these events. So we're finding lots and lots of them. So this is the absolute peak magnitude for each supernova. So we just take the peak brightness of each of them, and then we plot it against the decline rate, so how much it declines in 15 days past peak. And so it's some measure of how fast declining is. So these are the slower ones over here, and then over here you have the faster declining. And so now, this is what we now see when we go out. Each of these points is an object, a supernova that was discovered. And so there's a huge range in absolute magnitude. So from -20 to -12, so there's many orders of magnitude in flux. And we're now finding huge amounts of these. And so the key now that we're trying to figure out is how do you link these with explosion models. So we have these ones with white dwarfs with intermediate mass black holes. This would be this shaded region here. There are also model predictions for double white dwarf disruptions or white dwarf neutron-star mergers. And the key now is we're trying to get more of the observations to be able to try and link these different classes together. And so one way we're really, I think that's really promising for this is something called the Vera Rubin Observatories Legacy Survey of Space and Time, LSST. And so it's a new telescope that's being built and in Chile, and it's going to find about 10 times more supernovae than the best current surveys. And so just to give you an idea of the scale, here I'm showing the number of supernovae discovered as a function of time, so in years. So the first one was discovered in 1885. Then there were, these were pretty much all discovered by a man called Catastrophic, who people say was the grandfather of supernovae. He looked at photographic plates, so no digital stuff obviously back then, and found new events. Or sorry, this one here, this supernova control. And then robotic supernova searches, CCDs. Once we discovered the accelerating universe with supernovae, obviously everyone wants to be involved, and the number is like drastically increased. So this is a few years old now, but the numbers just keep going up, and LSST will be 10 times more than this. So one of the limitations, though, is we can find all these supernovae, and then if we really want to study them, we have to be able to observe them with other things. We have to be able to get like follow-up data. In particular, we want to be able to get spectroscopy, because that can tell us about the different elements that are present. And so one way that I'm involved in is with this foremost spectroscopic telescope. So traditionally, when you went to take a spectrum of a supernova, you'd go out and you'd put a little slit down on the position of the supernova, and you could disperse the light for like a single supernova at a time. But you can imagine if we're finding hundreds of events a night, that's not possible. So this is so some of these types of telescopes exist, but this is a game changer for the transient fields. This is the 4-meter multi-object spectroscopic telescope, foremost. And so what it is, it's multiple little fibers. So you can see them just moving there if you watch. And so each of those fibers can be positioned on an object in the sky over 4 square degrees, and then we can take a spectrum of each of them at the same time. And so there's 2,500 fibers in this 4 square degrees. Now there aren't actually enough supernovae to put on 2,500 fibers, but there's other people doing galaxies or stars and that kind of thing. And so we all share a single pointing and get different objects. So we reckon we can get about 200 supernovae at one time with this. So it has, there's obviously a lot of interesting engineering going into it as well, these fiber positioners. But the key thing is that with foremost, everywhere that this new search telescope points, we'll be able to get the live supernovae, and then we can also get the galaxies of dead supernovae, which are interesting for studying them. Okay, so that's kind of a whirlwind tour of supernovae, and then in the rest of the talk I was going to discuss gravitational waves, so I'm happy if there's any questions. I don't know if there's anything right away to the end. No, okay. All right. So, gravitational waves, as I said, some of you heard something of this earlier today. So these gravitational waves were predicted by Einstein back in 1916 in his theory of general relativity. And so there are ripples in space-time caused by accelerating masses. So you can see two stars orbiting in a binary system here, and they're releasing gravitational waves. So it's ripples in the space-time continuum that Einstein predicted, and he never thought would actually be possible to observe. But in an experiment starting, I guess they started planning it in maybe the 1980s, and it finally made a detection or came to fruition in 2015 with the LIGO Virgo gravitational wave detectors. It now has been possible. So some of the most interesting or strong events for producing these are binary black hole systems, binary neutron stars, and binary white dwarfs. So these are some of the most dense events and massive in the universe. We can also get signatures from asymmetric quark lap supernovae. And so what happens is we have two stars in a binary system, and then the gravitational waves are emitted from the system, and then they start to lose energy and they start to spiral in on each other. And this causes the binary obviously to decay. And eventually, in some cases, certain types of stars, you can actually get an explosion that we can see. So like the supernovae, we can see an explosion from these events. Okay, so I'm going to look in a minute at these gravitational wave detectors and some of the events. But there was also indirect evidence for gravitational waves going back to the 1970s. So Hulse and Taylor discovered a pulsar This is a rapidly rotating, highly magnetized neutron-star. So they observed that it rotates, a pulse arrives every 59 milliseconds from this source. And then from studying systematic variation in the pulse arrivals, the fact that it spins tells us that it's in a binary system. And so what you have is a pulsar orbiting around another neutron star, and then you get the radial pulses along this direction. So we're fortunate that we're, say, Earth is sitting over here, and that we're sitting along the direction of this change in radial pulse. If we're looking at a different angle, we wouldn't be able to see it. And so from this, then they said, okay, if we can they basically use the pulsar as very accurate timing, because you're going to see this pulse very frequently and very accurately. You can try and see if you can see the orbit shrinking from the release of the gravitational waves. And so that's what they went out to do. So this is in years here, so this is the date, and this is the orbital phase shift, so how the orbit decays in seconds. This is how many seconds it decays over 8 years. So it's a very small amount, but you can see that it has changed. And then in more recent observations, you can see the very gradual decay of the orbit. And then these are the data points are the points, and then this grey line is the general relativity prediction. And you can see that there's amazing agreement between them. And so this is the first indirect evidence that gravitational waves were taking energy away from the system. And they were awarded the Nobel Prize in physics in 1993 for this, for the discovery of a new type of pulsar, a discovery that has opened up new possibilities for the study of gravitation and for making these measurements. So this was the first evidence that, yes, it was likely that gravitational waves did exist, but it wasn't, and we weren't able to observe them directly. Well, people wanted to see if we could. And so the Laser Interferometer Gravitational Wave Observatory, LIGO, was developed. So you can see that they're situated these two yellow points here. So these were the first ones. Now Virgo is also contributing. And more recently, there's a Japanese telescope, Kagra, that has also come online. And so these are different gravitational wave interferometers in the universe, on Earth, that are looking for gravitational waves in the universe. And so if you want to go about trying to design a gravitational wave detector, you want to design something that's able to measure the stretch and strain of the gravitational wave. It's going to pass through the Earth. I actually don't have the movie, but there's another movie you can see of like the Earth wiggling as they pass through. And so that's what happens. They're passing through us right now. We just don't notice them. You need really sensitive detectors to try and detect them. We also produce gravitational waves, but again, the signal is very, very small. Okay, so how would you go about trying to detect a gravitational wave? We use something called an interferometer. So you shine a laser out here, you reflect it off two mirrors with this beam splitter that will be shown here. The arms are 3.5 kilometers in length, and then they're bounced backwards and forwards many times to try and increase the path length. And then they're combined back on this detector here. And so then you combine them. So this is now simulating as if a gravitational wave is coming through it. So you get tiny little movements in these mirrors, which are going to slightly change the path length. And then you get constructive and destructive interference on this detector. And these are really, really tiny signatures. So they have to try and control for seismic noise, for trucks going past the detectors, weather, anything and everything. And so the mirrors are suspended with, basically has to, it's in, I think it's the world's best vacuum. It has to be very highly designed, that's why it's taken so many decades to try and understand and try and design. They also, the fact that they have two different interferometers at different positions gives them confirmation that if they see something in just one, that it's not just a truck going past on the road outside. They're actually getting a simultaneous detection. And so in September 2015, they actually made their first detection. You can hear. The frequency goes up with time, so you get an in spiral, you get an increase in the gravitational wave signatures. This is from the LIGO Hanford, and this is the LIGO Livingston. The two different detectors detected the exact same waveform, which is shown here. So this gravitational waves. And so you see the increase in frequency. And so from modeling this, they're able to determine that it was a 36 solar mass black hole and a 29 solar mass black hole that combined to produce a more massive black hole. And so it's very exciting in general that they were able to find this, discover this, but it also can tell us about black holes in the universe. It tells us now, we know that black holes from about 8 to 80 times the mass of the sun actually can merge. And they radiate away gravitational waves, so a few times the mass energy, or the mass of the sun is radiated away in mass energy. And so one of the key questions then people are trying to understand is, like, did these objects here, did they merge from something smaller, or were they formed like this, or where did they come from? Are these from the collapse of massive stars? There seems to be some kind of limit of what's like you need a very massive star to collapse to produce a very massive black hole. So then have ones merged and then they need to merge again to produce the bigger ones. There's lots of questions that these observations have opened up. So originally these, you can see it very well, there's kind of purpley ones on the bottom, and they were the original ones that were discovered in electromagnetic radiation. But these LIGO Virgo black holes are quite different. So again, a Nobel Prize was awarded in 2017 for these discoveries, or this discovery to three physicists. However, I think this is probably one of those cases where you really want to start thinking about a Nobel Prize for a larger group. So there's huge teams involved in these kind of experiments. These just are some of the groups that were involved in designing these experiments over the years. Okay, so that was the merger of two black holes, the first detection, and since then there have been many discovered. But I'm an observational astronomer. I want to be able to see the light from these events. And so you don't expect to see anything from two black holes because everything just merges. There's no light expected to be released. But there are models of neutron-star mergers. So neutron-star mergers are also very dense events, not as much so as black holes. But there are predictions that you should actually be able to see electromagnetic radiation from these events, so from these collisions, and that they should also produce our process elements. So in August 2017, it was around lunchtime in Europe. It was bright, and we got an alert that there had been a gravitational wave detection by LIGO. And it looked like this. So it's quite a different sound. You can even tell by the length. So I don't know actually the time axis, but it's a slightly longer length of time that it occurs over. The other one was like a fraction of a second. This is a couple of seconds. And this just depends. So they have LIGO has a certain frequency range that it can observe over, and so it has to be when the gravitational wave. The frequency of the gravitational waves is within that region that we can observe it. Okay, so they did like models of numerical general relativity instead of just listening to it and figured out that it was two neutron stars with the most likely scenario for it merging. And then, even more excitingly, then 1.7 seconds after the gravitational wave detection, we got a burst of radiation and was seen by two high energy satellites. These are both ones in space. So NASA's Fermi satellite and ESA's Integral satellites. They both detected gamma rays from this. At the same. So at the moment they just announced that we've also found something at roughly the same time. We didn't know yet whether they were the same event. And so they estimated then this is the gravitational wave. This is the gravitational wave merger. position here, and this is the start of this gamma ray burst signature, as seen from one of the events. And so what they do is, with the gravitational waves, they can tell us approximately where on the sky the gravitational waves were coming from. So they can triangulate back, because it was detected by more than one detector. And so this is just a projection of the sky onto the surface of a sphere. But what we see is that LIGO found this region, Virgo in Italy was also operating. And so it said, okay, it's from this region, and then these are the gamma ray burst signatures, this blue one and this one. And so by combining then all the different signatures, or signals, you can say, okay, this is the most probable region of overlap. And so then search the optical and near-infrared telescopes started to go out and to tile out this region of the sky. So it was about 18 square degrees, 31 square degrees. And so within 10 hours, we actually found the new event on the sky. So you can see that here. So you have this is the galaxy of the event, and then the new transient was discovered here. So this is a new image, and this is an old one. So we always compare it to an old event to see that there was nothing there before. And so this was really quick. So this was like 11 hours after the gravitational wave was found. And so then we started to get loads and loads of observations. If you could pick out, it's just here. This is just a stack of all the different images. And so you can see it gets red really quickly with time. It starts off really blue and then gets red. And so this is dependent on the conditions in the ejecta or the material. And so we took loads of images, we took loads of spectra, and we really tried to constrain what was going on. So I think it's exciting just in itself, because it's the first time we've been able to hear and see an event in the universe. But you can also ask about the R process elements. And so these are the red ones shown here. They're elucidated apart in our process. The ones that we think, the ones of interest you might know, are like gold or platinum. We wanted to ask where were these produced in the universe. So to get these kind of elements, you need very high temperatures, so greater than 10 to the 9 Kelvin, and you need lots of neutrons produced by very neutron-rich isotopes. So you need about greater than 10 to the 22 per centimeter cubed. And so you need these kind of conditions. And so there were two hypotheses. One was that they were produced by import collapse supernovae, so the collapse of massive stars. So we expect them to produce neutron stars in the centers, really neutron rich. Or another place where you might expect neutron stars, or a lot of neutrons would be neutron star mergers. So we need high temperatures, plenty of neutrons, heavy seed nuclei. And then one of the key things is we need some kind of explosion. So there's no good producing them, things like gold, and then it's just stored in a rock somewhere. We need it to be spit out into the universe, so the next generation of stars could be produced to have the gold that we have on Earth today. And so we took, so from the spectra and from the modelling, it was pretty conclusively shown, or I would say moderately conclusively shown, that there were our process elements produced in this event. So the black here is the spectrum, so the observed spectrum, and then you have two different models. So red is with these R process elements, so cesium and tellurium, and then blue is without. So you need it to try and fit the spectral features. And so then there were further modelling that also showed another R process element, strontium. Okay, so this was the first ever detection in both light and gravitational waves, so it was a big deal. It was in all the major science and journals and news. And so it was very exciting, but obviously we've only seen one event so far, so we'd like to go out and get more of them, so to see more of these mergers occurring. They made a lot of movies, so it's nice. A lot of graphic designers. So what kind of questions then do we want to ask? What kind of physics questions can we answer? So we've got one event. We don't know how diverse they are. Do they all produce our process elements? What kind of mass ranges do they have? How common are they? One interesting thing that we now know does happen is neutron-star black hole mergers. We've seen these, but do they all look alike? Can you get different mass black holes? Do they always have a high energy counterpart? Do you always see gamma rays from them? We don't know. And then, are they the main source of heavy elements in the universe? And these are process elements. So we're very excited. So let me show you. So this is the different gravitational wave detectors. So LIGO, the original ones, this one in Italy and this in Japan. And they divide up into different observing runs. So they can't run all the time because there's lots of engineers and they need to do updates and all this kind of thing. So these colored regions show when they were observing as a function of time. And then this gives the kind of distances in the universe. This is a megaparsec they can observe to. So the first detection were made back here, and then in so here, in this O2 it's called, the second observing run was when we had the neutron-star merger. Then we had O3, we were really, really excited. Thought we were going to find not many of these events, but at least one. But there was nothing of interest. So these are 5 of the high probability events. So they have very boring names, but it's just the date and letter. And then these are like projections of the sky. And so these shaded regions show where they predicted from triangulation and the signal to be coming from. So they're quite large regions. They were much larger than the first one we detected, and so they were really hard to try and follow. So unfortunately, O3 was a washout. We actually didn't find anything of interest. However, we're very excited now about O4. It's currently running since May. I get alerts on my phone when there's new events. But unfortunately, well, we have a schedule. I don't have to. So somebody has to wake up in the night, but we don't do it every week. And we haven't found anything since May of interest. And so it's going to run, we've got another year and a bit, it's going to run until early 2025. And then they're going to turn everything off again, and then they'll do more upgrades to look at the greater regions in the sky in 05, which will be from about 2027 to 2029. And so they'll be a lot more sensitive. We will get a lot more, just we'll be looking at a larger volume. And so we're doing this with big collaborations, it's a big European collaboration of a few hundred people. And we have time at radio telescopes on the James Webb Space Telescope, the Hubble Space Telescope. We're going to try and get all the observations possible if we get another event. That's really exciting. So hopefully there will be news on some of these detections. Everything's public, so it should be announced if we do find anything very quickly. And then just in the last minute or two, I just wanted to mention what I think is going to be a very exciting future missions. This is LISA, the Laser Interferometer Space Antenna. It was approved in 2017. It's due for launch in 2034. And so what it is, it's 3, if you can see them here, these 3 spaceborne laser interferometers. So it's putting the LISA, the LIGO detectors into space. They're separated by about 2.5 million kilometers. And so the key thing is, because they're in space, they're not influenced by other low frequency sources on Earth. And they can target a different frequency range. And so LIGO and Virgo have been looking at these kind of frequencies, and the things you get here are binary inspirals. We haven't seen any supernovae, but you'll be able to study all the resolved galactic binaries, so tens of thousands of white dwarf systems, stars spiraling in on supermassive black holes in the universe with this. So I think this will be very exciting in the 2030s as well. And it's a really cool experiment as well. All right, so that's pretty much the end of my talk. So to summarize, we've seen a lot of excitement in the last couple of years. We've seen new types of supernovae, these faint and fast blips. We've observed large samples for trying to understand improve cosmological measurements. And we've also got the birth of multi-messenger astronomy. And so I think the future is bright with all these new telescopes and instruments for transient astronomy in the next 10 years and beyond. Okay, thanks. I'm happy to take any questions.
when you had when Neutron was operational, it also had distances. How do you choose what distance that you're looking at?
So do you mean on this one?
Yes.
Yeah. So sorry. These are so it's not specific. These are the upper limits for the distances. So they don't know yet. It's anything below either 100 or 140. So it's not shooting it. It's just anything up to that.
I wanted to ask about LISA when you mentioned with LIGO and Virgo there being so many complications of it running all the time. What about LISA when it will be far away in space? Will it be able to run just for a certain small period of time as well, and then?
No, I think the aim for that, I guess, one of the hopefully benefits of space is that there's a lot less interference or things. Well, if anything goes wrong, there's nothing they can do. But so they've got to design it so that it works from the outset. So it will run, I believe, continuously once it's up there. So I think it sounds crazy, but they have done tests already where they've actually shown that they can operate with smaller ones. They've sent smaller individual ones up and measured the lasers and everything, and it does appear to work. That's why it's been approved now.
How do they know what direction they came from? The gravitational waves.
Oh yeah, so they so if they have more than one, they can model it, and so they can model the direction. So yeah, it could come through the Earth, or it could come from space. But I think so. There's one slight offsets in the timing can tell you. So they're separated. They're on each side of the US, so they can measure the timing, and then they can combine that information. You get much smaller, what we call the contour regions of where they come from if you have a third telescope. So for that previous event, we did have constraints from Virgo, which helped as well. Yeah.
For the detections in light, is it just luck that they're observing that part of the sky where it's happening, or do they have predictions as to where to point to?
Yeah, so we got these. So what happened was once we got these predictions of where on the sky, so this little region which is about 30 square degrees, all the telescopes essentially in the world just started looking at that region. So it's still quite large. And so what they did was, so you can imagine when you look in that region, some of this galaxy, there's a lot of empty space as well. And so what they did to start with was to start to just observe the galaxies, so any nearby galaxies. So you actually get a prediction from the gravitational waves. It's shown down here. So you get this is megaparsecs of the distance. So you get a prediction from the different detectors of what distance this object will be at. And then you can start to figure, so you know some of the galaxies are at that distance, so you start looking with those ones. And so that's how they found it so quickly. Yeah.
Also, when you said about comparing the images that were 20 days ago and then the one that was taken as new and the object was visible there, would if it were in part of the galaxy that wasn't photographed before like this or not, is that was it now luck that they had a picture of this 20 days ago, or?
Yeah, so somewhat, yes. So now what we're trying to do for some of the searches is we're trying to keep up that kind of database of the old pictures. So a lot of the sky has been surveyed to quite deep. The problem is different telescopes use different, slightly different wavelength regions for their filters, green or red. And so it's hard to kind of cross-calibrate. So ideally now what the searchers do, this big transient facility, we just keep surveying the whole sky, and then we're ready if anything new appears. Yeah.
So in these sort of detectors, how do the gravitational waves cause interference with the light?
So they're completely separate. Is that what you mean?
Because I think you had the diagram or the film where you were using an interferometer to shine it or to measure kind of two different sources of light and see how the presence of a gravitational wave causes interference.
Yeah. So in that, the gravitational wave, it's stretches kind of squishes and stretches space-time, but in two different directions. It's got two polarizations.
So it's like it kind of, compresses the distance the light has to travel in order to.
Yeah, so from that, and that's because, so the arms are like this, they're at 45 or 90 degrees from each other, and so one of them is like stretched and one of them is pushed in the other way. So from that you can constrain it.
Also with the LISA detectors, because they seem to be in a triangle, which the original like LIGO isn't, so will that use a different sort of principle to detect gravitational waves, or is that not done yet?
So it's the same idea, so it's the same interferometry, the kind of matching up of paths, so like constructive or destructive interference from the path lengths changing. Obviously you have to set up different detection software because you're using a triangle versus two detectors at right angles to each other. But I think this is the most stable configuration if you want to kind of slide it together. They've designed this. But yeah, you need different software, but it's the same idea. It's also lasers in space. Yeah.
I wanted to ask, you said, unless I understood you wrong, that whenever there was a detection of a gravitational wave, within a second, basically, all the telescopes were pointing that way. And if that is such a quick reaction, is there not many false positives then with gravitational waves? Because before it's even announced or anything, there have to be checks.
Yeah, so sorry, those ones are different. That was what this was asking. So for these ones, so these ones that got it within 1.7 seconds, they just have they've really large cameras, or the detectors are really large. They were just looking at the right place at the right time. For these ones, that's how they detected it. That may not happen again. We were very lucky.
Actually, I might just ask it before we get off, or anyone else has any other questions. The way you showed the accuracy of GR as a measurement, other modern theories of gravity, like MOND or whatever, do they also kind of fit into that range, or is GR unique in its accuracy?
I don't know for sure, but I reckon this would be one of the things that anyone designing like a modified theory of gravity would want to try and also match up with. So I would reckon it would have, if it was to be believed as a theory, it would have to agree with those measurements.
So they all have like similar amounts of accuracies to the data?
I'm not sure exactly, but like I would say there's a lot more wiggle room in the MOND theories, so you can, don't want to be too skeptical, but there's a lot more wiggle room in them, so I think you can design them to be, you can get ones that match.
Okay, if that's everything, I want to say thank you again for putting this up. Please.